In section 4, we are going to talk about solving systems of 3 equations. So up until this point, we've been solving systems with 2 equations and 2 variables. Now we're going to talk about solving systems of 3 equations with 3 variables. So our 3 variables are going to be x, y, and z, which means it can only be graphed in 3 dimensions. So we're not going to be able to use graphing to solve a system of 3 equations. What we have to do is a combination of elimination and substitution to solve the equations. So it's 3 steps in order to solve a system of 3 equations. The first one is to eliminate one variable from 2 pairs of equations. The second step is to then solve that system of 2 equations, and then step 3 is to substitute the 2 known values back into an original equation to find the third. So the process of solving a system of 3 equations isn't necessarily more difficult than what we've been doing, it's just going to be more time consuming. So in our first example, we have the system 3x minus 2y plus 4z equals 35, negative 4x plus y minus 5z equals negative 36, and 5x minus 3y plus 3z equals 31. When you are doing your first step and you are trying to decide which which variable you want to eliminate from 2 pairs of equations, you want to approach it the same way we do a system of 2 equations. You want to find the variable that's the easiest to eliminate. So I typically go off, is there a variable that's got a coefficient of 1? So a variable that's just x, just y, or just z. Those are going to be typically the easier variables to eliminate because you will only have to multiply that equation. You won't have to multiply 2. So if I go ahead and number my equations 1, 2, and 3, I notice that in equation 2 I have a 1y. So I'm going to use that equation to eliminate y from using equations 1 and 2 and then equations 1 and 3. So the first thing I'm going to do is using equations 1 and 2. So we have 3x minus 2y plus 4z equals 35. And negative 4x plus y minus 5z equals negative 36. So in order to eliminate y here, I need to multiply my second equation by 2. So we have 3x minus 2y plus 4z equals 35. And then we have negative 8x plus 2y minus 10z equals negative 72. We're going to still add our equations together like regular elimination. So we get negative 5x minus 6z equals negative 37. So that's just the first part of step 1. The second part to step 1 is now to eliminate y again. I've already used equations 1 and 2. I have to use every equation once. So it means I have to now use equation 3. So we'll have 5x minus 3y plus 3z equals 31. Now I need to decide which equation I want to reuse. And I'm going to be reusing equation 2 because, again, it just has the 1y. So negative 4x plus y minus 5z equals negative 36. Now I want to eliminate y a second time. So I'm going to be multiplying that second equation again, but this time I'm going to be multiplying it by 3. So we're going to get 5x minus 3y plus 3z equals 31. And then we'll have negative 12x plus 3y minus 15z equals negative 108. We add, the y's cancel again. We get negative 7x minus 12z equals negative 77. So all of this work is part of step 1. We now have two systems of equations. We have that negative 5x minus 6z equals negative 37, and we have negative 7x minus 12z equals negative 77. When you eliminate a variable, you want to make sure that the two equations you have have the exact same variables in them. So we have two equations with x and z only. This is the system that we're now going to solve in step 2. So we have negative 5x minus 6z equals negative 37, and negative 7x minus 12z equals negative 77. Now, unlike step 1 where there's typically going to be an easier variable to eliminate, when we get to step 2, it's not going to be as nice as the system of equations we've been seeing. We'll most likely have to multiply both equations, and we'll have to multiply by a negative a lot of the times. It's not going to mean that we're going to have to do it every time, but it is going to happen more frequently. But if I look in this system, I can see that my z's are actually going to be easier to eliminate, because I can make a 6z a 12z by multiplying that first equation by negative 2. Now I do have to multiply by a negative here because my z's have the same sign. So we'll get 10x plus 12z equals 74, and then negative 7x minus 12z equals negative 77. So we're going to add, the z's are going to cancel. We get 3x equals negative 3, divide by 3, and we get x equals negative 1. We have now solved for our first variable. Now to solve for my second, I go to that system of equations I got in step 1, and I choose one of them to plug x in to solve for z. And just because the numbers are smaller, I'm going to choose that first one. So negative 5 times negative 1 minus 6z equals negative 37. We get 5 minus 6z equals negative 37. Now we're going to subtract 5 from both sides. We're going to get negative 6z equals negative 42. Divide both sides by negative 6, and we get that z equals 7. Now we've solved for two variables. Now we have finished with step 2. So our final step, step 3, take the two variables I have now solved for, x and z, plug them into one of the original 3 to solve for your third variable, which in this case is y. Now, when we go back to our original equations and you're trying to decide which one to plug them into, I look for the system where the variable you're left to solve with has a 1 in front of it. So that's going to be equation 2 because it has a 1 in front of the y. So we have negative 4 and then times x, negative 1, plus y minus 5 times z, which is 7, equals negative 36. Negative 4 times negative 1 is 4 plus y minus 35 equals negative 36. Combine like terms, we get y minus 31 equals negative 36. Add 31 to both sides, and we get that y equals negative 5. So we can leave our solution just like this, x equals y equals z equals, just like we did a regular system of equations. You can also write your solution as a point, and the way you write it is x, y, and then z. So just like a regular coordinate point is x comma y, 3 dimensions, it's x, y, z. So our final solution is negative 1, negative 5, 7. So it doesn't matter the order in which you initially solve for each variable. When you write it as a point, it always goes x, y, z. Second example, we have 4x minus 3y plus 6z equals 18. negative x plus 5y plus 4z equals 48, and 6x minus 2y plus 5z equals 0. So when I'm looking to see, I'm going to go ahead and number my equations 1, 2, and 3. When I'm trying to decide which variable to eliminate in step 1, I'm going to go ahead and eliminate x because I have just a coefficient of 1. It may be negative 1 in this case, but it's 1, and it actually is going to still be the easier variable to eliminate. So I'm going to use equations 1 and 2 first, so 4x minus 3y plus 6z equals 18, and then negative x plus 5y plus 4z equals 48. We're going to be multiplying our second equation by 4. So the first equation doesn't change. Then for our second equation, we get negative 4x plus 20y plus 16z equals 192. Add them together, the x's cancel. We get 17y plus 22z equals 210. So now I need to eliminate x a second time, and now I have to use equation 3 because I haven't used it yet. So 6x minus 2y plus 5z equals 0. And now I need to choose which equation I want to reuse, which is going to be equation 2. Negative x plus 5y plus 4z equals 48. This time we're going to be multiplying the equation by 6. So again, our first equation doesn't change. And then for our second equation, we get negative 6x plus 30y plus 24z equals 288. Add the equations together. X's will cancel. We get 28y plus 29z equals 288. So now I have a system of equations with just y and z. And this is going to be the system that we solve in step 2. So I'm going to write my system that I'm going to be solving. 17y plus 22z equals 210. And 28y plus 29z equals 288. Now, unlike that first example, when I got to step 2, I had a variable that was easy to eliminate. Here, I don't. I can't easily make a 17 a 28 or a 22 a 29. So I'm going to have to multiply both equations in order to eliminate a variable. And when I'm trying to make that decision here, I'm just going to go with the variables that are smaller so that I'm dealing with smaller numbers. So unfortunately, 17 and 28, the smallest number they go into is their product. So I'm going to multiply my first equation by 28 and my second equation by 17. And since they are both positive, I do need to multiply one of them by a negative. And it doesn't matter which one you choose to be negative. So I'm just going to make the 17 negative. So when I multiply my first equation by 28, we'll get 476y plus 616z equals 5,880. And then for the second equation, we'll have negative 476y minus 493z equals negative 4,896. So we might end up with some very large numbers when we get to step 2, but our final answers are going to be nice. So my when I add, my y's are going to cancel. and we'll get 123z equals 984 divided by 123. And we're going to get that z equals 8. Now I want to plug that into one of the two equations I got from step 1 once I eliminated them to solve for y. And I'm going to go ahead and choose the 17y one just because the numbers again are smaller. So 17y plus 22 times 8 equals 210. We end up with 17y plus 176 equals 210. Subtract 176 from both sides. We get 17y equals 34. Divide by 17, and we're going to get that y is 2. Now we've solved for y and z. We're now going to do step 3, which is to solve for x. Now I need to choose which of my original 3 equations I want to plug y and z into in order to solve for x. And even though the second equation has a 1 in front of x, it's a negative 1, which I typically like to avoid, but just so that you can see an example of it, I am going to do it here. So negative x plus 5 times 2 plus 4 times 8 equals 48. So negative x plus 10 plus 32 equals 48. Combining like terms, we get negative x plus 42 equals 48. We're going to subtract 42 from both sides. So we get negative x equals 6. Divide both sides by the negative 1. And we get that x equals negative 6. So again, I can leave my solution just like this, or I can write it as a point, negative 6, comma 2, comma 8. So far, in the 2 examples we've done, you have noticed that I have not had any decimal answers for a system of 3 equations. And just like a system of 2 equations, I didn't give any decimal answers. I'm not going to do that for systems of 3 equations either. So if at any point you're doing a system of 3 equations and you get a decimal, go ahead and ask me for help if you can't figure out what your mistake is. Last example. We have 5x plus 4y minus 5z equals negative 10, 6x plus 15y plus 12z equals 24, and negative 4x minus 10y minus 8z equals negative 16. So looking at this system of equations, there is no nice variable to eliminate. I don't have any variables that are a coefficient of 1 already, which means that I now need to figure out which variable is the easiest to eliminate in terms of keeping my values small. And if I look, that's going to be x, mainly because 4, 5, and 6, there's a lot smaller of a number they all go into versus 4, 10, and 15, and 5, 8, and 12. So I'm going to choose to eliminate x. So when it comes to the first set of equations I'm going to do equations 1 and 3. So 5x plus 4y minus 5z equals negative 10, and negative 4x minus 10y minus 8z equals negative 16. So the reason I chose 1 and 3 is that the x's already had opposite signs. And the smallest number that 4 and 5 both go into is 20. So I'm going to multiply the first equation by 4 and my second equation by 5. So we get 20x plus 16y minus 20z equals negative 10. And then we have negative 20x minus 50y minus 40z equals negative 80. Add the equations together. The x's cancel. We get negative 34y minus 60z equals negative 90. Now for my second set of two equations, I haven't used equation 2 yet, so 6x plus 15y plus 12z equals 24. And then I'm going to reuse equation 3. And again, because the x already has a negative in front of it, and that way I don't have to multiply by a negative. In this case, when I'm trying to eliminate x, 4 and 6 can both be made into 12. So I'm going to multiply my first equation by 2 and my second equation by 3. So I don't necessarily have to multiply the equations by the other variable's coefficient. So we get 12x plus 30y plus 24z equals 48. And then negative 12x minus 30y minus 24z equals negative 48. So when I add my equations together, x, y, z, and my numbers are all going to cancel, and I'm left with 0 equals 0, which is a true statement. So even though I was able to eliminate x from one set of pair equations and get a system that had just y and z, when I tried to do it a second time, all of my variables eliminated and I was left with a true statement, which tells me that for this system of equations, the solution is infinitely many solutions. So just like with a regular system of equations, with a system of 3 equations, we can get infinitely many solutions. We can also get no solution. So if all of my variables had canceled and I had been left with an untrue statement, like 0 equals 12 or 0 equals 2, that would be an instant of no solution. So very similar to a regular system of equations, you can get infinitely many or no solutions from a system of 3 equations. And it happens in a similar way. Please let me know if you have any questions about systems of 3 equations, whether that's choosing which variable to eliminate in step 1, solving a system of equations in step 2, or even plugging those in to get your final variable solution in step 3.